Okay. Any questions on the metric model? Okay, again, let me remind you, there are two approximations of the metric model. One of them is when the average delay per demand is computed. The second approximation is the implicit assumption that the depot has infinite capacity in terms of repairing. So that there is no additional waiting time for each item, but there is only this mean time. Okay. Now, in the metric model, you see that the allocation problem that we talked about, remember what was the allocation problem? Well, here you are supplying lower installation, and the problem is, let's say that this guy asks for certain items. Each of them orders certain quantities. If the higher installation has sufficient quantity, then there is no problem, because each of those items will be sent. Now, problem is when it doesn't have the sufficient quantity, then there is also an allocation problem. So the allocation problem is a problem where even if the quantities that you desire is not satisfied, then how are you going to ration the amounts that you are going to send? How are you going to decide on the amounts that you are going to send? Well, certain problems are easily solved. In metric, this is easily solved because when you have S-1 as policy and continuous review, you are assuming that, if you remember Poisson process, no two demands are going to come at the same instance. So you will always have one of them having first priority. So you have first come, first serve. And if you have first come, first serve, it means that you are going to satisfy the demand in terms of first come, first serve. So it is easy. Now, the problem is when you have periodic review systems where you let the lower installation order any time that they want in the beginning of a certain period. The problem is they order at the same time. So there is no one lower installation which orders before the other. They all order at the same point in time. So how are you going to make this allocation is not a very simple question. It creates a lot of uncertainties with respect to decisions. Now, the next paper that we are going to see makes an assumption in terms of how allocation can be done. I will talk about that assumption. But it also describes a system where there is a depot. This is an Epperen-Schrage 81. There is a depot which doesn't hold any inventory. So the system structure is as follows. Here we have the supplier. Let's say it can be the manufacturer. Then there is a depot here. And then you have warehouses. Which is fed by the depot. So the standard understanding of the distribution system is as follows. The supplier is going to feed the depot. The depot is going to keep stock, okay, and then feed the warehouses. So this is the standard understanding. Now, in the system that they consider, they assume that depot will not stock anything. So the depot is simply going to be a transfer point. So this is a cross-dock point, as they call it. Now, you probably have heard the word cross-dock. Okay, have you heard the word cross-dock? Now, cross-docking comes from a very simple idea. Dock is actually a place where you do the loading, unloading. So let's say that this is a docking area. So what you have is you have trucks getting near the docking area. So this is sort of a truck, a trailer. So the truck empties its load on the dock. And on the other side, you have another truck waiting. or you might have 2 more trucks actually. So what you do is, whenever you empty something here, you put it on this truck, or you put it on the next truck, so that the docking area is simply an area where you exchange the items from one truck to the other. So this is called cross-docking. You basically empty and then fill the next one, which is on the other side of the dock. So this is usually called incoming truck. This is the trucks here are called outgoing trucks. So what happens is that incoming trucks are coming from different suppliers. Outgoing trucks are going to go to different retailers or warehouses. But the key here is that an outgoing truck is going to carry items which are coming from different manufacturers. Whereas an incoming truck carries only items that are related to a single manufacturer. So you bring certain things from the factory from Bolu, another truck brings certain things from another factory in Samsun, but this outgoing truck to the market, supermarket, is going to carry part of the items that are coming from Bolu, part of the truck is full with items coming from Samsun or whichever the other city was. Okay, so basically this is the idea of the cross-docking. The term comes from there, and in this case, the depot, the transfer point doesn't have stock anything. So what do you gain with this? Well, you gain a lot of issues. One of them is that the depot, although is going to act like a storage point, you don't keep any stock there. Keeping no stock there means that you are not going to have an additional safety stock there. Okay? Remember, each time that you have another installation, you keep safety stock. Whereas by using this installation in a reasonable way, okay, you are going to lower the inventory. What is the key here? You have to be able to make the operations efficiently. Okay. This is what Walmart has done 20 years ago, actually, or maybe even less than that. This model actually came through the discussions with industry people who were thinking of doing it this way. And I think this was the times where Walmart was sort of growing. And so Eppen and Schrage simply mathematically modeled the issues that were going on after they learned from the industry people that this cross-docking is a suitable thing to do. Okay? So the model that we are going to see is simply going to model this structure where the depot doesn't hold any inventory. Now, so this is going to be like the continuation of the Eppen paper, which discusses centralization, decentralization. Now we have a third option. Okay? We are not fully centralized, but we are not decentralized as well. Okay? Because we have another level where we don't allow for any stock keeping. Okay. So this is what we're going to do. Now, of course, here you can say that, well, we have the allocation problem here. We have the allocation problem, but the interesting part is that every time that a load comes to the depot, you allocate it among warehouses. In other words, as you don't stock anything, that decision is going to take place at that instant. Okay? So this is actually one major idea of the paper, and I will talk about that in detail. Okay, so any questions on this? This is sort of a very typical distribution system, and we will hopefully analyze this in a little bit more detail. Now, I am going to go over this paper using the Eppen-Schrage 81 paper, which is in your recommended list, not required list. In your required list, we have this paper by Bolla Pragada, which is a shorthand version of the same model. And it is a little bit more general. So I will first give the initial model, but the notation and everything is exactly the same. So you don't need to worry. You will be able to follow that paper as well. That paper is, has more, actually, on Epen and Schrage. Okay. Now, at this point, I am going to bring in some notation. I'm going to assume that the lead time from the supplier to the depot is denoted by capital L. And the lead time from the depot to any warehouse is denoted by L. Okay, so I'm going to assume that everything is the same. Now, we are interested in minimizing the holding and backorder costs in the warehouses. So I'm going to assume that there is a holding cost per unit H in each warehouse, and there is a backorder cost per unit, which is denoted by P in each warehouse. So these are the cost parameters, and these are the lead time parameters. I'm going to assume that we have periodic review system, and I will assume that we review every period. Actually, the paper by Epen and Schrage contains also the case where you review the system once in every m periods. So what's happening every period? Every period, warehouses review their inventory position. They give orders, okay? And the supplier is going to release that order immediately. We are assuming that the supplier has infinite supply, okay? So it would release that quantity, and then the quantity will be first shipped to the depot, cross-docking point, and then will be shipped to the warehouses. Okay. Now, I'm going to assume that warehouse J has a normally distributed demand with parameters mu J and sigma J square. So normally distributed demand, which is reasonable, of course, if you are stocking Frito-Lay's potato chips, okay? Okay, which might be one of the possible products that we have here. Now, I'm going to denote the random variable of demand. This is the random variable denoting the demand in warehouse I at time t. And this is actually what we assumed, that this is normally distributed random variable with mean mu I and variance sigma I square. So E is going to stand for the demand. Okay? Note that the demand is stationary. Moreover, I am going to assume that EIT and EJT are independent. In other words, we are not going to assume that there is some kind of a dependency between demands of different warehouses, and there is no correlation among time. It is simply independent, identically distributed random variables for a given warehouse, and it is independent of the demand in the other warehouses. But in reality, we know that it's not. Okay? Now, think about what's happening when we are getting close to, let's say, Ramadan. Coca-Cola is making ads for Ramadan. Remember that they have sort of tables with colas and so on. So they start to sell a little bit more. And of course, what would you expect? If it sells more here, it is also going to sell more here. So actually, it turns out that in reality, these demands are not independent. And, but I will talk about that in a while. Okay, so this is the basic model. And so given this model, as we are reviewing every period, there might be a fixed cost of reviewing and ordering, but we don't care. Okay? So we assume that each warehouse is going to have to follow an order up to policy. So every period, they are going to check their inventory position and give an order up to level. This is their optimal solution. We know that. Okay? So it means that as demand is stationary, the order up to level is also going to be stationary. Now, the problem is, of course, the order up to level may not be satisfied. Why? Because you give an order according to our order up to level, but what's happening in reality? The supplier ships a certain quantity. The quantities arrive at the depot. Now, at the depot, at the time of allocating it to warehouses, those orders are not important anymore. Why? Because the depot is going to make an allocation among the warehouses so that the total cost is minimized. In other words, if this guy has ordered more, in the meantime, the demand might be realized and it might be low. So the ordered quantity is not necessarily the quantity that they are going to get. In other words, in this type of a system, the way that the system is managed as follows. The supplier actually looks at the inventory levels, give an order accordingly, and then when it comes to actual allocation, it is going to be a function of what you have at that point in time. Okay? It's not going to be a function of the quantity that is going to be ordered. So, although this is actually the order up to policy, now what we are going to do is the supplier, we are going to transfer this problem as the supplier's problem. Supplier will order up to Y every period, where Y is in terms of system stock. In other words, think about the following. You are operating this system, and the supplier, the depot, and everybody are members of the same system. The total cost that you want to minimize is the cost of holding and shortage, some of the cost of expected costs of holding and shortage at the warehouses. So in order to minimize that, you are going to have a system optimal level where you will be ordering up to that level every period. Why? Because demand is stationary, it doesn't change with time. So you are going to order up to the same level. There is no need to change that level. So let that decision variable be Y. So what is my decision problem then? My decision problem is to find this Y and at the same time allocate the stock to warehouses. I don't know how to do that allocation yet, but these are the two variables that I need to do. So I'm going to bring system stock to a certain level every period, ship the quantity that I recently manufactured to the depot. When the quantity arrives at the depot after L time units, I'm going to look at the inventory levels of the warehouses. I will allocate the quantity in such a way that the total cost is going to be minimized. Okay. Now this is actually what we are going to do. Any questions on this? Okay. Now let me start with the allocation problem. Okay. So the warehouse, yeah. Okay, we assume that. Okay, this is a good question because the question is as follows. Your friend has asked the following. The information, the inventory information is available at the supplier. Because we assume that system operates, the system that we are considering has a single owner. So everything is known ahead of time. Now, in general, we'll see that if it is not known, this wouldn't be the case, of course. Okay, so we assume that all the information is centrally available. Very good question, actually. I should have told that before. Okay, so so it means that when we have these two decision variables, we know everything. Okay, which in reality, of course, in case of supply chains, this may not be true. But we at least should know what we are going to do if we knew that information. So this is what we are going to see now. Okay. Now, the key issue to understand here is as follows. Remember, I said the holding and backorder shortage costs are identical in each of the locations. So what does this mean? The demands are different. So here we have, let's say, warehouse 1, and here we have warehouse J, and this is the inventory levels. This is the inventory levels. And when we do the allocation, and let's say that, well, I shouldn't say inventory level, and let's say that this is the demand function, cumulative Fj, cumulative probability function for demand. We know that both of them are normal, so the shape is going to be something like this, but the parameters are probably going to be different. Okay? So let's say that we have two warehouses. We do want to minimize the shortage and holding costs. Now, what is the form of the shortage and holding costs? Remember from Append's paper? Okay, you have normally distributed demand. Shortage and holding costs are the same. If we had a single warehouse, what will be the optimal solution? Remember, the optimal solution is the news vendor solution, where we stock everything up to a certain fractile. Okay, even if we have infinite horizon. Now, here it turns out that when you do the allocation, what you want is, you want to bring each of the warehouses to the same fractile. Given that P and H are the same, okay, you want to bring everything to the same fractile. So this is, of course, going to be Q1, or let's say, so here we have P divided by P plus H. Now, this is the ideal fractile, of course. Now, in the time of allocation, you don't have much choice. But the key issue is, how do you minimize the cost? Let's say that the following. Let's say that for one warehouse, you have a little bit above the fractile, and for the other warehouse, you have a little bit below a certain fractile. So in that case, what will happen is that you can show that if you give this unit to this warehouse, and if both of them are identical, then the total cost is going to be minimized. Why? Because you see that, remember, each time that you add another quantity, the marginal effect of that additional quantity is going to be smaller on the total cost. In other words, if you add another unit. So the optimal solution, if you have n warehouses and you have a certain fixed amount available, is to have everything so that you have equal fractals in every warehouse. So actually what I am doing is I am solving the following problem. Let's say that this H stands for holding, expected holding and backorder costs. So what I am minimizing is the following function. I am minimizing summation I from 1 to n, HI's, subject to the, let's say, xi is the stock, subject to summation xi is equal to a capital X. Okay, this is the problem that I am solving actually. So this is the total H, one of the H's is the expected cost of holding and back orders, newsboy type, okay, because there is no other cost. And so what you are solving is you are trying to solve the sum of these subject to a limitation in the total quantity. Why? Because at the point of allocation, you have a limited quantity that you are going to distribute. Note that you cannot keep it in the inventory. There is no inventory in the cross-docking point. So whatever you have, you are going to spread it out. If you have a lot, you are going to spread it out as well. If you have little, you are going to give it away as well. So when you try to solve this problem, the individual problem, if you didn't have any constraint, would like to have everything up to this fractal point. Okay? The P divided by P plus H, because that's the optimal point. Now, what happens if you have more? What this simply says is that if you have more, rather than putting all the quantities that are more than this optimal to a single one, you put everything one by one, one after the other, and distribute everything evenly, sort of. Evenly in the sense that the solution is of equal fractal. Now, how are we going to see this, whether this is true or not? Okay, and what I will do is I will give you, well, maybe on Thursday, I will describe this problem in a little bit more detail, or I'll just check whether you had, did you have something like this in your homework? Multi-level? I think you have one problem that I gave you now. Do you have this? Can I see the homework number 2? Okay. Okay, I think, can I have? Yeah. Okay, in homework number 2, the first problem is more or less, well, it looks like this one, but I think I have to make an extension on that problem in order to describe this clearly. Okay, because I thought that I gave you a problem like this. Now, but it turns out that I gave the deterministic version of it. Okay, now, again, if I repeat my conclusion here is that what you are doing in allocation problem is that you're solving a problem like this, where the P and H values across the warehouses are identical. So given that each additional unit that you store here or here is going to cost you the same thing, the solution that you are going to obtain for this is the so-called equal fractal rule, which means that whatever quantity that you have available, you are going to give equal share to each of the warehouses. So this is the optimal solution if you can apply that solution. Okay, so this is the allocation problem. Now, question is this always a feasible solution? In other words, can I always find a solution which is going to bring my inventory levels to equal fractals, so that they are going to have equal fractal solution? The answer is no, and let me explain you in a very simple example. So, well, let me give an example to explain this equal fractal first, and then I will give an example where we won't be able to stock everything accordingly. Okay, now let us say that we have 2 warehouses, and let us say that they are identical. In other words, identical means that they are both going to have the same mu and sigma. Okay? So let us say that the initial inventory, assume that L is 0 to make things simple. So now what I will do is I have a certain quantity at the depot, and I'm going to distribute this quantity in between warehouse 1 and warehouse 2. Let us say that I have 25 units at the depot currently and on the cross stock, and let us say that the inventory currently in warehouse 1 is 5 units and inventory in warehouse 2 is 12 units. Okay? Very simple. So if you are going to minimize the expected holding and shortage costs at the warehouse, how do you allocate these 12 units? Both of them are identical. Well, you make sure that both of them gets the same quantity in total. So how many units do we have in total? We already have 5 here, 12 here, 17. And we have 25 more waiting at the crossdock. In total, how many do we have? 42. So as a result, I want to end up with 21 units here and 21 units here. Now, why do I need to have 21? Because my cost is identical. Everything is identical. So having 20 here and 22 here obviously is going to increase my costs, because costs are not linear. Remember, the costs that you charge, we're talking about expected costs, are not linear. So you are going to give the same exposure for risk to both systems exactly. Exactly the same exposure to risk. So this is the ultimate solution that you want to have. So what does this mean? This means that you're going to ship 16 units to warehouse 1 and 9 units to warehouse 2. So this is the optimal solution for the allocation problem that we're talking about. Okay, now equal fractile actually means something like this, but as the means and variances are different, okay, the solution that corresponds to the same idea is called equal fractile. So what does it mean? It means that you are going to select a k value such that the mu I plus k sigma I values are going to be exactly, you are going to have a single k value, fractile value, which is going to be the same when you are solving this allocation problem. Okay, so the logic is exactly the same. Equal in the sense that if they were identical, then we're talking about equal quantities, but their mean and variances are different. So what you want is you want to cover the risk in the same way. That corresponds to saying that these k's are identical. So the optimal solution to this problem is such that you have a unique k for all the warehouses. Normally distributed demand. Okay. Now, so this example showed us that this is feasible. Now, let's give the same example. So, similar example, but I will only change the initial quantities. So you have exactly the same thing, but let the initial quantities be the following. Let I1 be minus 5, okay, and I2 be 14. Okay. 18. I'm sorry. Okay. So, again, all the information is the same. Now, what I'm going to do is I'm going to compute the system stock. What is the system stock? System stock is 25 plus 18 minus 5, which is 38. Okay, so that wasn't even enough. So 38, 40. Okay, let me make this 22. Okay. So system stock is 47, 42. Okay, so system stock is exactly the same. I wanted to show that it's exactly the same, 42. So what you want is you want to distribute everything in such a way that eventually they are going to be 21 units. But what will happen then? Unfortunately, as this initial inventory was very high, you are not going to achieve the equal fractile solution. So, unless, of course, if you don't make a transshipment. What is transshipment? Transshipment is the shipment that you do in between the warehouses. Okay? So equal fractal is a good solution, is the optimal solution if it is feasible. In this case, equal fractal solution is not feasible. Okay. So this is actually the key. Now, of course, what Eppen and Schrage did was the following. They assumed that at the point of allocation, we are going to have an equal fractal solution. So, assumption. At the point of allocation, an equal fractal solution is feasible. This is called the allocation assumption. So we call this as the allocation assumption. And of course, if you read the paper, they make a number of computations given different situations and so on, normally distributed demand, Poisson distributed demand, and show that this is actually a reasonable assumption under certain circumstances. Now, the key here is, of course, this is not a very simple way of measuring. I mean, these probabilities cannot be measured in a simple way, so they used a number of tricks to compute that probability, including something which is called Bonferroni inequality. I don't know whether you are familiar with that. It is something that comes very frequently in statistics when you are doing hypothesis testing, a number of them at the same time, and you want to make sure that there is some kind of a level of accuracy in all your tests. So it is not simply sum of the individuals because you use the same data and it is dependent. So Bonferroni inequality is used in those cases, and they simply apply this to this one to show that allocation assumption is reasonable under certain circumstances. Okay, so this is the main assumption that they make. They simply say that allocation assumption simply says that we are not going to have the cases of example 2. Okay, now we're ready to proceed once we know how to proceed. So what we have is, remember we had two problems to solve. The first problem is to find the quantity y. The second problem is to find the quantities of allocation. So we understand how we are going to do the allocation, but we need to actually show that in a little bit more detail. So for that purpose, we are going to define two quantities. Okay, so quantity number one will be V. V is going to denote the system stock, the demand over capital L lead time. So V is going to be sum over all J, T from 1 to L, J from 1 to N, of E sub JT. So what is this? This is the lead time duration, the capital L lead time duration. Let me, this is the depot. This is, excuse me, this is the supplier, this is the depot, and this is the warehouse. So this was L, if you recall, and this is lowercase l. Okay, these are the lead times. So we're talking about demand over lead time over all warehouses. So what's happening? So this V quantity is total system demand over the lead time, over this capital L lead time. And then we're going to define W as the demand, and it will have a subscript J. Wj is simply going to be sum of AJT over T from L plus 1 to L plus little l plus 1. So what is this part? This is the demand for warehouse J over the lead time from the depot, from the crosstalk point, to the warehouse plus 1, which denotes the review period, if you recall. Periodic review, if you recall, response time is what is important. So this is the response time of the warehouse J from the crosstalk point. Okay? So these are the quantities that we are going to use to describe certain things. So what's happening here, let me show everything on the timeline. Okay, so at the initial point 0, I'm going to bring my system stack to a level y. Okay? Now, after capital L lead time, what will be the system stack? Now, the actual stack, okay, now this is the total amount that I'm going to bring the system. So Y is inventory position, actually. Now, physically, at time L, what will be the physical stock available? Y minus V. But this physical stock is not only going to be available at the crosstalk point, but it includes the physical stock which is available at the warehouses. Okay? So there will be, some of these will be here, some of them will be where? In the, on the way or in the warehouses. Okay. And finally, I am going to make my final shipment here. And at time little l, capital L plus little l plus 1, I am going to charge my charge costs. So note that the quantities that I'm going to have here can only be affected by the order up to quantity that I have here. So what I'm going to do this is simply I'm going to analyze this cycle and give my optimal decision using this specific cycle. And note that this cycle is going to repeat itself. It will be exactly the same cycle, infinite horizon. So what I will do is I will take this cycle, minimize the cost per period for this case, which is going to minimize the problem, the problem in question. Okay. So here, note that I assume that I will be able to make an equal fractile allocation. Okay. So now, any questions on this? Okay, now it's time, actually, to find out this so-called equal fractile allocation. Now, let xi be the inventory, xj, be the inventory position of warehouse J after the allocation. Okay? After the allocation, so here, look at the timeline. I am doing the allocation. So we have 0 quantity available at the crosstalk. Everything is placed in the trucks. They are on the way to go to their warehouses. Plus, there are already certain amount on the way, of course. Okay? And this xj is simply the inventory position that is related to warehouse J. Now, one thing that you should see at this point, I'm going to talk about this later on, is the following. Now here, during this capital L period, although you are not going to change your decision with respect to total quantity, you carry all the units together. Okay? So, for example, this means that, for example, you can do the shipment with a transportation mode, which is going to minimize your total costs. Remember the paper by Eskigün? Okay? What they did is they used rail actually for this purpose, because they are carrying a huge quantity. So using rail is very meaningful. So you make a saving actually using this cross-docking point. What is your additional saving? During this capital L time period, you have not allocated the stock to warehouses. Okay? Because if you did direct shipment, what would happen? If you did direct shipment, you have to allocate everything here to the warehouses. Whereas you don't do any allocation until this point in time. So what happens is that you delay the allocation decision. Okay? What do you gain with delaying the allocation decision? Well, the uncertainty is less now because you only have little l plus 1 periods in front of you that you make a decision for rather than capital L plus little l plus 1. Okay? This is called statistical economies of scale. Okay? Because statistically speaking, you make a better decision because you delay your decision. This is the idea of postponement. This is the idea of many things that are available in the supply chain literature, and we are going to make connections. Okay. Now, let's come to this problem. So let xj be the inventory position of warehouse j after the allocation. So then summation xj, j from 1 to n, would be equal to what? Well, the total amount which is available, which is y minus v. Okay, remember? V is the quantity which is already demanded. So y is the system order up to level at time 0. Now, note that there are other new orders coming in which are on the way here. We don't include them. The quantity which is here and onwards, the echelon stock, is y minus v, and this is what you are actually allocating. So this should be equal to y minus v. And how am I going to represent this? Equal fractile solution. Equal fractile solution means the following. So I have j from 1 to n. What is the expected demand over little l plus 1 periods? It is simply little l plus 1 times mu j, open and large parentheses. I have a new value, or we can say I have a k value, which is the same for all the items. Then I'm going to write the standard deviation of the warehouse j demand, which is simply going to be sigma j square root of l plus 1. So you can now see that by imposing an equal fractile allocation, I would like to find this k value which is going to satisfy this condition. So from here I can write k. In the paper there is another letter, a Greek letter nu is used, but I'm simply using k. Now what is this k? K is simply y minus v minus summation l plus 1 mu j divided by summation sigma j, well, square root of l plus 1 summation sigma j, j from 1 to n, j from 1 to n. So you see that this is the optimal fractile, and we are assuming that this fractile point can be realized. So this is the solution of the allocation problem. So at this point in time, the decision that we make is going to be an equal fractile decision, and this is going to be the equal fractile multiplier that we have. And so we're going to bring all the individual stocks to this level. Now you can see that this might be violated because we might have sort of some stock, a lot of stock on hand for a given warehouse. So cross-stocking, then you have to make some transshipment. But we assume that this is a feasible solution. Okay, that's the allocation assumption. Okay, any questions on this? Okay, on Thursday, I will be probably finishing this and talking about extensions. And I will relate that to the supply chains, including the question that you asked about information, so on and so forth. Okay, any questions? Okay, I'll see you on Thursday.